Well, it's a great pleasure to be here to celebrate a really important piece of science that started and has been pushed forward in the UK. There are some housekeeping things that I need to say. First of all, I should say that I'm Richard Friend. I'm Professor of Physics at Cambridge, and I'm acting as chair for this event, and delighted to do that. Can I ask you to turn your mobile phone off? I should probably include myself in that, but at any rate put it onto flight mode. And more importantly, well actually as importantly, remind you that this event is webcast and recorded, and so your coughs and snuffles will be there for posterity. But more importantly, when we have the question and answer session at the end, it is important to wait for a microphone and to stand up if you want to ask a question so that we can capture that. There are no planned evacuations, so if the fire alarm goes off, it's for real. And there's a fire exit there, and apparently that's the one to use, that door there. So back to this evening's lecture. So Henry Snaith worked for his PhD in Cambridge, went to the École Fédérale de Lausanne in Switzerland, working on solar cells there, came back as a research fellow to Cambridge and then moved to Oxford, where he has created an incredibly exciting program of research on new materials for solar cells. And it's his recent discoveries and how he's turning those into real opportunities to transform the solar world that we're going to hear about this evening. So he really is the right person for all sorts of reasons to be awarded the Kavli Medal and Lecture. It's a relatively recently established award for the Royal Society, but it's one that is very important. It is awarded alternate years in the fields of science and engineering relevant to either the environment or to energy. So what I will do at the end of the lecture is present Henry with the scroll and a check and the medal. So without further ado, Henry, I invite you to give this year's Kavli lecture.
Thank you very much, Richard, for the warm introduction, and I'd obviously like to thank the selection committee for awarding me this award. Thank you, and also thank everyone for turning up this evening to listen to it. Hopefully, it's been worth coming for, but we'll see. So, I'm going to talk to you about photovoltaic solar energy. I'm going to start the lecture by just sort of highlighting where we are with photovoltaics globally, where PV is industrially, and then also go on to some of the new materials we've been looking at and how we're trying to discover things that are better, materials and solar absorber materials that are better than what we're currently using. So to start with, we'll take a sort of a world's view of power, if you like. Our current global power demand's about 16 terawatts. It's probably going to grow to around 30 terawatts by 2050, and we need to supply this power in some means. Of course, we're aware we currently generate most of our power from burning fossil fuels, and that's not sustainable for a number of reasons. It's been very useful to get us to where we are, but we now need to decouple from carbon and find means to power the world in a sustainable manner. So if we look at renewable energy and the sort of different potential that you can get from different sources, hydroelectric could give us 4 terawatts. That's quite a lot. That could be quite substantial, but it's not going to produce all the power. These are some other examples. And solar dwarfs everything. We could, in principle, if we covered the world in black solar cells and didn't worry about where we had to live, we could produce 36,000 terawatts. And if they were 100% efficiency. So that's not quite the case, but clearly there's a vast excess of power. Now, the easiest way to capture sunlight is in plants. We could grow plants, harvest them, and burn them to generate power. That's sustainable, it's carbon neutral. But the downside is plants are only about 0.3% efficient at converting solar energy into end-usable energy. They have to sustain themselves and their growth, and they're not designed just to produce energy. So we as humans have been trying to do something better for quite a while. The first example of something that could be called a photovoltaic cell is from 1839, so a little while ago, a few years ago, from Becquerel. And this photo cell consisted of sort of platinum electrodes in an electrolyte, and he found that if he shined light on one of these electrodes, he could generate a voltage and current. This was improved upon about 50 years later in what's starting to resemble a modern solar cell. This is a layer of selenium, a few hundred microns thick, sandwiched between a metal substrate and a thin gold leaf. So gold, when it's thin, is slightly transparent. The light comes through here, and this generated photovoltaic energy. It wasn't used to produce power, obviously. Fast forward a few years to 1950, and the first silicon solar cell was invented, and this is more similar to what's used today. This is a picture of probably a 1990s silicon solar cell, if you like, and I'm just going to briefly describe to you what this solar cell is. This is an artist's impression of what it looks like. It consists of a thick slab around 300 microns, so thick for someone working in semiconductors, quite thin for yourself. Your hair's about 40 microns thickness, so it's about 10 hairs thickness. You can see it. And I'm not going to go into the details of what this P and N type is. Other than the P type, we make the semiconductor positively charged, and that ensures that you can have current flow into the semiconductor. And on the other side, we make it negatively charged. That ensures current flows out. I'm going to come in a few slides' time to describe a little more details about the working of the solar cell. But don't worry yet. You can relax a little bit longer, I think. This is what modern solar cells, or reasonably modern solar cells, look like. And of course, you know you may not know, but the efficiency of converting sunlight to electricity is about 25%. So it's quite good. And this development of this technology has led to a massive growth in the installation of PV. And of course, you've probably seen PV panels on many roofs. You're aware that there's panels and solar farms being installed. This is the cumulative install capacity, global install capacity as a function of years up to 2015. The red is the actual data, and these lines are predictions. And what's been regularly predictable is that the PV installations have outperformed predictions, and this has happened year on year. And even the most ambitious Greenpeace predictions for installed PV have been outpaced. So we've had a massive increase in installation. On this linear scale, this looks as if it sort of comes out of nowhere, but instead of plotting install capacity on a linear scale, we plotted on a log scale, or increasing in orders of magnitudes, factors of 10, then this looks linear back to the 1980s. So it's actually been many decades that we've had this growth in PV installation, and we expect it to continue. Now, this has been driven largely by a dramatic reduction in price. So since 1977, this is one means to cost solar power. It's dollars per watt. It's how much dollars do you spend on making a module or installing the power for each watt you get out. And it originally cost $76 in 1977. That's gone down to about $0.3 US today, even a little bit lower in some places. So what does that mean? Dollars per watt doesn't really mean very much. What it means at this cost, it means it's economic to install massive solar farms. This is an example in Dubai. And the cost of electricity from PV, this is a rather cluttered slide. If you just look at this little column here, this is the lowest bid for a recent installation in Dubai. It was last September. 2.4 US cents per kilowatt hour is the cost they're pledging to sell the electricity for. So if you've looked at your electricity bill recently, you'll note it's a lot more than 2.4 cents per kilowatt hour. If you had it in cents, it's in pence, obviously, or something like that. But the global average cost of producing electricity from coal is about 4.6 US cents per kilowatt hour. So here, in sunny locations, PV is already cheaper at producing electricity than producing it from coal. So we've reached this tipping point when in some places it makes more economic sense to install PV than it does to install any other cost. Sorry, I had a little circle around there if you can't see my pointer. So that's all well and good, and it looks like we should probably all just go home and be happy that the job's done. But that's not quite the case, because PV only produces electricity when the sun's shining, and what we have to do is then be able to store that and reuse it. So there's a lot of effort on electricity storage in batteries, and I'm not going to talk to you about that because I'm not an expert in that. I'll just say a few things. Firstly, that it's essential for a society that can be powered off PV. We obviously also need electricity storage. Batteries is one way. There's many other ways as well. In terms of the cost of electricity storage from batteries, it is currently much higher than the cost of the generation from PV. But the main reason is batteries have not yet been scaled to the same level. There hasn't been a factory produced that produces a gigawatt of storage capacity until present day. And this is just an example of Tesla's gigafab, where they're basically producing many gigawatt hours of battery capacity. But this is the first gigafab. So we expect battery technology, the price of storage will go down. And this makes it even more, the likelihood of PV installation being a major source of power even more likely. So I'm now going to come on to the PV cell technology. And this is, I'm going to go through a very basic science lesson. So I apologize for anyone who is a scientist in the audience. You can close your eyes for a little while. And anyone else, I hope this is going to be slightly understandable. A semiconductor is a material that can be switched from a conducting to a non-conducting state, a conducting to an insulating state. And the reason why it can be switched from conducting to insulating is we have something which we call bands and band gaps. This blob or dark grey box here, this is representing what we call the valence band. This scale is energy. This is the energy that the electrons have when they're bound to the lattice. It's the highest energy the electrons have in the crystalline material, which can be a semiconductor, when they're bound to the lattice. When light is shone on this material, electrons can take that energy from the light. And if they've got enough energy, they can be promoted or given energy and go into this higher band that we call a conduction band. And basically, you can think of it as a particle of light, a photon coming in and knocking an electron, and it gives it enough kinetic energy that it's now free of the lattice and it can move through the crystal. And it's these photo-excited electrons that conduct in a solar cell. And if we can extract them, if we can get them to conduct through this material into an external circuit, then we can generate current from absorption of sunlight. Now, a solar cell also generates voltage. Electrical energy is current times voltage, so this is obviously an important factor. And the voltage a solar cell generates is basically equal to, it's slightly less than, but more or less equal to this band gap of the semiconductor. So if you want to absorb sunlight, you have to have a narrow band gap because you need to absorb a lot of the energy of the photons. If the light has energy of lower energy than the band gap, then it passes straight through the material. Now, I'm going to come back to this in a minute. And as I said, the power is voltage times current. So if you just hold this notion that to absorb as much sunlight as possible, you need a narrow band gap, but to generate a voltage and a big voltage, you want a wide band gap, you end up with a slight compromise. On this next slide, I'm showing here, this is the solar spectrum. This is the irradiance, how many watts per square meter we have at different wavelengths. This region here, this is the blue region of the spectrum at 400 nanometers. These photons in the blue region have high energy. They carry about 4 volts of energy. This region here is the infrared. So the visible, we can only see in this short region here up to around 700 nanometers. This region here is the infrared. These photons have lower energy. They carry about 1 volt of energy. So if we make a solar cell or solar absorber to capture this sunlight and convert it to power, we need the solar cell to absorb up to around this 1 volt of energy. It generates current from absorbing all these photons, and it generates about a volt. And that band gap in electron volts is about 1 eV. And the maximum efficiency, because we're throwing away energy from these photons we don't absorb, and there's also heat lost from the higher energy photons, the maximum conversion efficiency is only about 33%. That's if we make an absolutely perfect solar cell, that's how efficient it is. So current technologies at 25, 26% are already getting very close to the theoretical limit. I'm now going to show you another rather busy graph. This is a graph of the efficiency of different solar technologies, and each of these little dots is a different type of solar cell. So firstly, you can see from this the research community is very busy. We haven't just got one type of solar cell, we've got tens of solar cells, and all these different technologies are vying to become commercial or be dominant in the industry. Silicon, the current dominant technology, are these blue lines here. So they're sort of middle efficiency. All this stuff down here is what we call emerging photovoltaics. This technology is still in the lab, and it's trying to up in efficiency to become competitive. What you also notice is there are solar technologies that even go up to 46% efficiency. So I've told you that the maximum efficiency is 33, but now I'm showing you a graph with 46%. So if you're wondering why, I'll now explain, and I'm sorry if this is going to be slightly confusing to some people. If I mentioned that a single absorber throws away energy as heat from the higher energy photons and lets the lower energy photons pass through, so you throw away energy there. If we can actually stack different materials on top of each other and capture the high energy photons in a wide gap semiconductor, the middle energy photons in a middle gap semiconductor, and the low energy photons in a low gap semiconductor, we can put those cells in series and extract more energy from the solar spectrum. And in principle, in 3 junctions, we could in principle get up beyond 50% efficiency. So we can go from 33 up to 50% in the limiting factor. In 2 junctions, we can go up to around 46% in theory. So this route is known. This route's been known since about the 1980s, and this is where all the really high efficiency cells come from. The technologies that are used are based on these compound semiconductors, all these letters, indium, INGA, aluminium, A, they're different elements that form compound semiconductors, and they have to be grown in multi-layers. Each of this color is a different material, and the crystallographic lattice, the crystal planes running through this layered device have to all align. And that means they have to be grown very, very slowly and basically by expensive means. So the cost per square meter of making one of these really high efficient, even 5-junction cells is about $40,000 a square meter. So even at 46% efficiency, that's not going to work. But the question is, we know how to make efficient cells, we know how to make cheap cells. Can we combine this together? Can we find new materials to make these sort of device stacks but be no more expensive and even less expensive than silicon? So I'm just showing you the periodic table here, and silicon sits here on the periodic table. So these are all the atoms and elements that we've got to play with when coming up with new compounds. Actually, even though there's a finite number of elements, there's an almost infinite number of ways we can combine these atoms. There's not an infinite number. Someone could calculate what is the number, but it's very, very large. And we're nowhere near exploring all the possible compounds there are. And in fact, silicon is just an elemental semiconductor. If we go down, the world's record solar cell is made from a compound of gallium and arsenide, and that makes 28% efficient single-junction cells. What you can also move out further and go to a compound of cadmium telluride. This is one of the world's best technologies for low cost, but it's not that efficient. And what we've been working on and what we found is make a very good solar cell, elements or compound semiconductors with lead or tin as the main metal. And these are perovskites, and I'm just going to briefly describe to you what they are. So perovskite is a word you may not have heard. I hope you will hear it more and more, and I hope you'll be putting perovskite solar cells on your roof at some point relatively shortly. But the perovskite itself is calcium titanium trioxide, or calcium titanate. That's not a semiconductor, that's a mineral. But if we make any material with this structure, we call it a perovskite because it adopts the same structure. And the ones that we found work very well in solar cells, as I said, are those that have lead or tin as the B site, and as this X site, we find halides, iodine, bromine, or chlorine are very good. At the A site, we use this ion called cesium. And in fact, this material, cesium lead triiodide, was first presented in 1892. So again, it's not a new material. We just never really tried it properly in solar cells. So we were fortuitous enough to stumble on this. Actually, I'm not going to go into the details, but cesium lead triiodide makes a very nice material that's a really good solar cell material if your solar cell's at about 300 degrees Celsius. Now that's a little bit too hot, and you don't want to put energy into heating your cell to make it work. And in fact, this cesium ion, at lower temperatures, this material falls out of the perovskite structure and changes crystal structure. You don't want to have to run your solar cell at 100 or 300 degrees. Unfortunately, ideally, we'd go down to francium, but you probably are aware that francium's a little bit radioactive, so that sort of puts a stop on that. We can actually go off the periodic table, if you like, and this now broadens these materials into what we call hybrid crystalline compounds, where we take inorganic materials, metals, and we mix them with organic molecules, ions, and this is methylammonium. And methylammonium lead triiodide makes a very, very good stable or room temperature stable crystal perovskite that works well in a solar cell. And we can go to a slightly larger ion, formamidinium. And more recently, we've been mixing these different ions and different halides and different metals together to really see what happens. But this is the sort of flexibility of this crystalline structure. We can mix all these ions together and it changes the properties. So in terms of the evolution of this perovskite research, it started a while ago in 1892. But what I show here are the publications. These are academic publications as a function of year, and in perovskite solar cells. And it wasn't until 2012 till this field kicked off, if you like. And last year alone, we had 2,000 academic publications. So it's become a rather busy area, and we're making lots of advances. With that has driven this new technology here. That's this little line here that's red, yellow circles with yellow dots with red around it. That's now competing. It's 22.1% is the best efficiency for a single junction cell. This technology is relatively simple. All we do is layer 3 basic materials together. We have a conducting sheet on one side that also lets sunlight through. We have our perovskite layer, and this thickness is only about 300 to 500 nanometers. So your hair is 4,000 nanometers, and this is about a tenth of the thickness of your hair. So it's a pretty thin layer. And then on top of that, we have another material that conducts the charge out of the solar cell. So this material interacts with sunlight very strongly. It's relatively easy to process. We just mix some powders together. We have the metal halide precursor, the cesium halide or methylammonium organic halide precursor, mix them in a solvent, and we can then print them down and make solar cells. I mentioned before that we can mix these ions, and what that means is that we can change the color of this material, and changing the color means we can change the band gap, and this now makes it very applicable to using in these multi-junction solar cells. And I will just show you one example of a device where we've got a wider band gap perovskite on one side, and then processed on top is a narrow band gap perovskite. So this material's red, this material's black, and this is the wavelength. The light is absorbed. This is the responsivity of the solar cell in this front material up to around in the visible spectrum. Then the infrared, it's absorbed in this rear material. So these all perovskite. This is a perovskite tandem solar cell. These are up to, the best we've achieved is about 20%. Some people have achieved up to 23% with this sort of structure. So we've got a technology that looks like it's going to work as well as silicon, and we can now make multi-junction cells. So we could put our sort of head to the ground and drive forward and try to deliver a standalone technology that's going to compete straight away with silicon. But as you know, silicon's had a massive industrial scaling process, and it's going to be very difficult to launch a new technology into that already existing market. So better to do that. If you can't beat them, join them. And actually this makes a lot of economic sense as well, is to use silicon, use it as our infrared rear absorber and process the perovskite cell on top. And in doing this, we should be able to increase the efficiency. And in fact, we've done some calculations based on operating perovskite cells and operating silicon cell. The efficiency of this perovskite cell theoretically is about 20% efficiency, so it's not unrealistic. This silicon cell is about 22% efficiency. And if you combine them together, you actually get nearly 32% efficiency. Now, this is not a real measurement. We're not yet at 32%. We hope to be soon. This is the responsivity of a real tandem cell, and the efficiency here is about 24%. So that's about where we are in practice, but where we expect to get in the near future is up towards 30% efficiency. And that's not the limit of it either. We can calculate that we can go beyond 2 junctions, for instance, to 3 junctions in this instance. And this, with 2 perovskite cells on top of silicon, we could push the efficiency up towards 36%. So the ceiling is much higher than where it currently is. And this ceiling, this is a realistic value if we can just integrate the current technologies correctly. This has just shown you some of the progress. This is some of our work and also other work in the academic field. Since 2014, the efficiency of these tandem cells has shot up tremendously. These are specifically the tandem cell devices. So it's a very good concept to reach high efficiency. I'm going to penultimately talk about some of our commercialization efforts. So as well as trying to drive this forward from a basic research standpoint, we're also trying to actually make a real product out of this and something useful that can really drive the industry, the PV industry, forward. And we're doing this through Oxford Photovoltaics. It's a company I founded a few years ago, where we are solely focused on producing perovskite on silicon tandems and driving forward the technology. And key challenges have been proving the stability. And I'm not going to go into the details of this, but this is just to give you an illustration of the sort of challenges we have when we want to deliver a new technology, especially something like photovoltaics. Photovoltaics have to be guaranteed for 25 years. So that's 218,850 hours. That's quite a long time to do an experiment in the lab for, and obviously we have to therefore rely on an accelerated environmental stressing. And this is excerpt from one of the IEC stability tests, and basically a series of cells or modules go in the top, get tortured by various means, and hopefully work when they come out the bottom. So this has been a large focus of the company to get the technology ready and surpassing these standards. And this is an example of a few different standards: 200 thermal cycles from -40 to +85 degrees, 1,000 hours light soaking at 60 degrees centigrade, and 1,000 hours at 85 degrees with 85% relative humidity. So if it's a really hot day and your modules are deployed somewhere humid, they may be subject to these sort of conditions. This doesn't now mean the technology is ready for market, and in fact this is a stage gating, and typically the manufacturers of PV will subject their modules to 3 to 5 times these IEC standards. So this is something that's work in progress. The next step for us commercially is to go from cell technology towards a manufacturable module technology. And fortunately, silicon wafers come in one side and they're 6 inches. So they're 6 inches by 6 inches. That's not actually very large for an area to scale up for manufacturing. But of course, they have to be produced at a massive throughput and a very high yield. And to do that, we've recently purchased a facility in Brandenburg in Germany that was run as a CIGS, copper indium gallium diselenide solar cell pilot facility. And we bought this and we're repurposing it to do the first stages of manufacturing and the scale up towards manufacturing of the perovskite solar technology. So to finish on a relatively light but a note, I believe, what does the future hold? Well, almost free power from the sun. So PV will continue to advance. The cost's already very low. over the next decade it will get lower. So it will be the cheapest source of power available ubiquitously or over most places in the world. Of course, we need to learn to store it and to redistribute it, and that's another part. On another note, what will this lead to? Hopefully, it will lead us away from pollution towards a sort of a utopic world. You might not like the look of this world, but you might have to live in it or go up a mountain or something. And hopefully, we'll all have electric vehicles and be able to charge them as well. On a final note, a sort of a interesting note, if you like, if we have free power or very inexpensive power, it does mean we can do a lot more things. And this is an example from a company, Seawater Greenhouses. They develop greenhouses for growing stuff in arid countries. So they pump salt water in and let it fall over big sponges in these greenhouses, and it evaporates. And in evaporating, it cools the inside of the greenhouse, which means it can be 20 degrees cooler than the outside. So this enables farming in places that would otherwise not be able to have farming. And if you have enough power and it's cheap enough, you don't mind how far you've got to pump the water to do this. And of course, so you're producing food, power, and clean water at the same time. So that's the sort of ideological result of PV power. But on that note, I will thank you, and I'll just put up sponsors and funders of the research that I've done, and thank you very much.
Well, Henry, thank you very much for that wonderful lecture, which I think was splendidly intelligible. We have lots of time for questions.
I did a bit quick.
I can see a hand there. Do please stand up when you ask a question so that we can capture you on camera. Yes.
Thank you.
And if you would like to, say who you are.
My name is John Bell. It's a very simple question. How efficient is chlorophyll at converting solar energy?
Well, that was what I presented at first. So in terms of quantum efficiency, in terms of taking a photon of light and converting it to some usable form, it's very close to 100% efficient. But in terms of power conversion efficiency in a plant, it's less than 1% efficient. So it's not very efficient at producing energy. It's not. We need to coat a vast area of our land. If we wanted to use plants to produce power, we'd have to use a very much larger area of land than we do using electronic devices, photovoltaics.
The answer rather confuses me. How does that compare to what you're doing?
These technologies...
Is chlorophyll really brilliant? Or?
No. Chlorophyll, unfortunately, is very good at what it does for a plant, and it's obviously evolved over millennia. But in terms of usefulness for producing usable power for human use, it is not anywhere near as good as photovoltaics.
I think there's a question towards with a pink shirt. Yes.
Thanks. Peter Corley from Imperial College. I'm interested in the geographic spread of these things. So fossil fuels have given countries like this a huge advantage because we've had coal and oil and so on. With a large population density and not that much land, you're in really bad shape, and in northern latitudes, you're in very bad shape for solar. So you're talking about a huge shift of economic advantage to the south and to desert areas, obviously, as you describe in Dubai. What prospects can you hold out for Northern Europe?
Well, I slightly disagree with that because the cost of generating power is the cost of the installed PV, and that is coming down and down. So at the moment, it makes total sense in very sunny places. The UK, for instance, compared to Dubai, we get about 2.5 times less sunlight, but it's not 10 times less. So if the cost of installing a solar farm in Dubai is 2.8 cents or 3 cents per kilowatt hour, it'll be something like 8 cents per kilowatt hour in the sort of latitude that we are here. So it's not orders of magnitude more expensive. So that means as it goes down in price, the cost of generating actually very soon, within a decade, will be cheaper than producing electricity from coal, even in the UK. Now, in terms of storage, you store kilowatt hours, you don't store unit area. So the cost of storage, you'll require less storage in Northern Europe per square kilometre of PV panels. But of course, the cost per watt will be just the same. So actually, I think the continuing improvement in efficiency of industrial PV and reduction in cost will make it totally economic anywhere in the world to produce PV power. The opportunity is not necessarily where the resource is, but who enables that technology. Which countries have the companies that are developing and deploying the PV and in essence driving the whole power industry. So that's where the wealth, if you like, and the economic strength will come from. It'll actually be having the companies or the countries have the countries having the companies which are commercializing this and driving the industrialization. Now, at the moment, a large fraction of the silicon PV is in Chinese companies, and that's exactly where these new opportunities, for instance, with this sort of perovskite technology or other new clean energy technologies, actually give an opportunity for a different country to gain dominance in that area. So it's by no means sealed up. At the moment, the PV industry is probably a few % of the size that it will be when we reach terawatts PV generation. So it's the companies of today are very small compared to the companies in a few decades' time. So even if they're geographically in China mainly, there are also a number in the US. It doesn't mean that's where the final dominant companies will end up.
Can I just
I'm not disputing any of that. I suppose my question is really about land area.
Yeah.
Because land area per person here is very small, and clearly, with the best will in the world, it is a low density power source.
Well, I did a back of the envelope calculation, so that is all this is, which I'm about to quote. But actually, this wasn't my calculation, but the amount of land per person in the UK that's farmed is about half the land mass. So we've got about 4,000 square meters per person per capita, and about 2,000 of that is farmland. I calculated that at 20% efficiency to produce all our power, so electricity and our current power generated from burning fuels and transport, we need something like 100 square meters per person. So it's not insignificant, but it's on the order of 5% of our farmland or something like that.
Just to put a fly in the ointment, we do have winter as well as summer.
Yeah.
And it's about sort of 7 times less sunlight in January than in July, isn't it, Henry?
I refrain to say no comment. No, very good point. So, I mean, of course, it would be better to have more sunlight, and it would be very good to have good relationships in Europe so that we can have power cables coming up from Spain, etc., and not have to bicker over import tariffs on electricity.
Yes.
That wasn't my final point.
I'm not very good at spotting in which order the questions came. I could see Cyril. There's a question at the back there. It's always harder to see people at the back. I'll come back.
Hi, John Bassett here from UK Power Networks. So obviously the PV is you install it, but before that you've got extraction of resources from mining, and after you've got recycling. So I wonder if you could give some comments on silicon technology and also new technologies and how it impacts those two aspects as well. Thank you.
Yeah, I mean, I think that there are a number of examples in the past where there's been some, for instance, bad pollution from slurry from soaring silicon put into rivers, etc. And that's not good, obviously, for the industry or for anyone. And it takes away largely from the benefit of PV. So the whole life cycle analysis has been done and is implemented on installed PV modules. They do get recycled, or there's a mandate to recycle them, and certainly any new technology being deployed will be recycled. So that has to be costed in. For instance, First Solar, which is one of the companies that deploys cadmium telluride solar cells, cadmium is not a very nice material, and they do recycle their modules. It costs about 2 cents, I believe about 2 cents per watt peak is the cost addition due to recycling. So it's something that has to be costed in, and they may be more or less fixed prices, so they're sort of a baseline price of what is what's required. Now, in terms of absolute energy input, for instance, in silicon, the ingots have to be made by heating to a few thousand degrees for tens of hours, and it's a lot of energy that goes into it. One of the selling points for our new materials are that they're processed, we don't heat them beyond 150 degrees, and they're dried very quickly. There isn't this long thermal input. That's easy to make that argument, but silicon has scaled so much, the ingots are made at such a scale, actually per wafer the energy input's relatively small. So you can overcome a lot of things that look like fundamental cost barriers simply by scaling, and that's something we've learned from many industries, but certainly the silicon PV industry is a very good example of that. So it'd be very easy for me to stand up and say we've got less energy input, we're going to be the much better, superior technology, but at the end of the day, if you scale enough, the cost per unit goes down and the real input per unit goes down. So it's very real. It's not just economics.
So one of the measures for that is how many years or months does it take collecting electricity from an installed solar panel to repay the energy that was used to make it and install it. For silicon, it's what, 18 months now?
Yeah, depending on where they're installed, it
Yes.
can even be down to a year. So, yeah.
So long as it's sort of working for 25 years, a year is a fairly small upfront carbon dioxide penalty. Cyril, towards the front.
Cyril Hilson from a variety of organisations. Congratulations, not just on your lecture, but also on your research progress, which has been quite admirable. I'm interested in stability. I've worked with cesium and haven't found it to be the easiest of materials at times. I wonder if you can give us a number for where we've got to at the moment on half-life.
I can't give you a precise number. What we work for is these IEC targets, and for silicon PV, when they have 3,000 to 5,000 hours on these accelerated measurements, they're happy to stamp them with 25 years warranty. We're working towards 2,000 hours at the moment. So we've surpassed 1,000 on many tests, working towards 2,000. So we're on the route. But the other important note there is until you've actually got a full-scale module that's produced on a production line where you're not doing it at a research scale, let's say, you can't properly test these things, and it's likely that you will have introduced more errors than you would when you've got a very well-controlled process with very well-controlled deposition of layers in these devices. So we're expecting it to be there when we manufacture it, as we currently stand. But we obviously, this is a key consideration and something we really have to demonstrate and prove and gain confidence of the people who are going to be manufacturing it and deploying it.
Well, I'm used to being pleased when the efficiency is the same tomorrow as it was yesterday, so
yeah.
I congratulate you.
Question there. And there is one right at the back, so it will come. But let's start with a question towards the centre, 2/3 of the way to the back.
Sorry, thank you. If you'll humor a question from a non-scientist. So in relation to the question about mining, I've heard a lot about global sand shortage and sand piracy. Now, I'm not a scientist, and I don't know if that's where you get your silicon from, but in terms of the ecosystem, in terms of the supply that was hinted at before, as well as any comments around superconductors, so how to get your electricity or your company's electricity to its consumers, if you maybe just provide a few comments.
So I'll answer those two questions. Firstly, about shortage of sand. I can't. I mean, I've never heard anyone complain there's a shortage of sand compared to the amount of sand that we use in building construction. Making glass. I mean, glass is 4 millimeters thick, 4 to 6 millimeters thick. Silicon wafers are a few hundred microns thick. I don't think sand shortage is going to be a problem for PV. So, I mean, there is serious concern over some rare earths like tellurium that's used in some solar cells. But again, these fears for elemental shortage are usually not very well founded, and it means they may not be being produced at a suitable level currently, but when there's the demand, we can go out and mine them. And currently there's enough stuff in the Earth's crust that we can make PV for many, many thousands of years. The other question, I've forgotten what you asked now, actually.
Just about the superconductors.
Oh, in terms of for long-range power transport. For that, I presume you'd need a room temperature superconductor. This is something that's still elusive, but would be a great innovation, and people are working on towards these. I don't know if you've got... But that's not for long-range power. That's if you wanted a superconducting cable. For long-range power, you can use high-voltage power cables.
Well, and I would add that high-voltage DC is about 5 times more efficient than AC. You can, I mean, the quoted figure is 5% loss per 1,000 kilometres for high-voltage DC, and that's been made possible through advances in high-voltage electronics that make it possible to switch voltages, DC voltages from silicon carbide, gallium nitride. It's all possible. So I
thank you.
away. Yes.
All right,
So
thank you.
It's very likely that certainly within Europe, political instability aside, that we should easily be able to have a reinforced grid that enables transmission of electricity throughout from sunnier places to northern climates.
Okay. As an economist, the answer that supply will create or demand will create the supply is quite satisfactory. So thank you for that.
There was a question right at the back on this side.
Suzanne Wallace. I'm a PhD student over at Imperial. I had 2 quick questions, if I can be a bit cheeky. So firstly, you said that your modules are about 6 inches. Why is that? And I really would assume if you're printing, you could have any size you want.
Because we're processing on silicon, we're scaling up the manufacture of perovskite on silicon. Silicon wafers come at 6 inches in size. That's how big the ingots are and how big they're diced to. So that is industry standard. So we're not going to try and reinvent that. That is what current silicon industry wafers are. And one reason is for monocrystalline, that's how big they make these single crystals by pulling them out of a big vat. And if they go bigger, you can grow bigger crystals, but they are more likely to have faults and defects in them. So this turns out the ideal size for yield. In terms of assembling into the solar cell, having cells this size is also quite a good way, again, of improving yield, because the bigger the cell, the more likelihood that you'll have a critical failure on it. So the silicon industry started at 4-inch, went up to 6-inch, and it may be there for a long time. We're not going to try and change that. We're just processing on top of that. Ultimately, in an all-perovskite technology, if we do away with silicon and just try to make a thin film module that's perovskite, then yes, that could be any size. You still have an issue that you've got to manufacture on that size and get high yield.
Is it almost like your Christmas lights situation where one bulb blows and they all blow? And whereas if you've got them in smaller sections, you have less of a problem?
Yes.
My second small question, if I may, was related to your tandem technologies. So obviously it seems that they are a much better technology than a single junction in terms of getting high efficiency quite quickly. But do you see the cost increase for that type of architecture? Is that significant enough that it may be difficult to balance that with economy of scale? And if there's a big increase going from 2-terminal to 4-terminal? I mean,
this is so if I just sort of discuss on the case of putting perovskite on silicon, the cost of the current silicon cell is about half the cost of the assembled module. And then when you deploy that module is about half the cost of the total installation. So there's something called balance of systems, which is the cost of the frames, the electronic inverters, the land, the permits. And that costs actually more than the cost of the module. So your cost of your cell is maybe 1/5 of the total cost of installed PV. Now, so there's some room, therefore, if you're increasing the overall power output, to increase the cost, but you wouldn't want to treble it or quadruple it. So it has to be a small fractional increase, and it can't be much more expensive, but we don't think that will be. On the thin films, there may well be a market for a very inexpensive product that is just a single junction perovskite cell, but it's probably not utility scale power generation.
Okay, there's a question towards the front. There we go.
Thank you, Professor Henry. It was a very good lecture. I am part from India, CSR NPL. We have lots of power, solar power. The question is, going from 24% to 31%, what are the limiting factors that you see in efficiency improvement?
To get there,
Yeah.
a lot of it is optical, making sure we absorb enough light in each layer or the right amount of light. And then there's electrical. We still have losses between the absorber layer and the charge extraction layer, so the contacts we put on the absorber layer, there are losses. The charge recombines. We lose energy at those contacts. So that's where there's space to improve these things.
Okay, we're generating quite a few more questions, so let's move through them. One to the left there, my left. Yes.
Sure, I'm Ben Martinoga, a science journalist. So you've talked a lot about utility scale generation, but some people see a solar future where truly distributed power, so it's on every building material, clothes, devices. Do you see perovskites playing into that? Is that part of your vision?
Yeah, they certainly have a prospect there. So we've focused on the high efficiency tandem cells. We think that's where where the current biggest market is, so more of a commercial decision. In terms of building integration, one thing we have been working on is making these single junction perovskite cells semi-transparent. So instead of absorbing all the light, you actually allow a fair amount of the light to pass through. Of course, the efficiency drops because you're absorbing less light, but then these could be a replacement for glazing. It's something that is probably going to come in the industry. It's called, as you no doubt know, it's called building integrated photovoltaics, where you actually basically use the PV in the building facade. That has been an industry that's been promising to grow for the last decade, and it hasn't quite taken off. Now, there is legislation coming in place in Europe that's going to mandate new buildings having, much less energy usage per square meter, and even reduce carbon impact. And this, one way to do that is to produce electricity in the building. So I'm sure we will see this. The timeline is difficult to predict. This technology absolutely could do that, and that probably wouldn't be the perovskite on silicon. That would just be the thin film perovskite. One advantage there, or one disadvantage with wafers, is that they are 6 inches, and you can see them when they're on a panel. People are implementing means to make them more discrete, but basically they're there. And if you don't want your building to look like a satellite, which lots of people don't, some people quite like it, then you want something else. You want just a thin film glass glazing. And that's what the thin film option can deliver.
A question over there.
My name is Yasser Hassan, postdoc from University of Oxford. I have a question for you, Henry. You have shown the periodic table, and you talked about alternative ways of combination between atoms. As a chemist, when I play with these parameters or these combinations, what's the characteristic list? When I checked, I will reach the moment. I say, I got it. What are these characteristics that I am looking for when I check all of them? I said I got the beautiful materials that the whole world is aiming for.
This is an interesting question that I hadn't asked Yasser to ask me. So Yasser is one of my postdocs in my research group. One very I'll reel off a prepared answer to this. One very important question on materials discovery is, how do you test those materials to see what they're useful for? And we'd love to have a machine that we could just mix these compounds together, stick them in the machine, it tests them in a gazillion ways and tells us this is a good superconductor, this is a PV material, this is a good solar cell material. Unfortunately, that doesn't exist, but what obviously does exist is metrics that we can use. And one metric for solar cell materials, which someone not used to working in it will find this quite ironic, is that luminescence, how much light emission these materials give when you shine light on them, is a very good measure of how good a solar cell material it is.
Okay, question at the back. 2 questions at the back, but one at a time. No.
Simon Dowland, University College London. Your talk covered mostly, for the new technologies, perovskites, but there are a number of other technologies which are competing for that space. And I was just wondering if you'd like to comment on where you see organic photovoltaics in relation to perovskites, particularly in regard to the fact that in recent years they've pushed through the 10% barrier. So
one of the sort of critical measures that's become apparent, especially over recent years, to deliver high efficiency is low electronic disorder. And you know how this is measured. I won't go into how it's measured, but basically this is how ideal your semiconductor is. Now, a semiconductor, not like organics, but amorphous silicon, which is the non-crystalline form of silicon, this has a large electronic disorder. And this means the maximum efficiency those solar cells can ever generate is about 13%. It's what they're at. They'll never get more than that. And because crystalline silicons come down in price so much, that's never going to compete for utility scale. Now, organics have continued to deliver on improvements over the last decade and still continue to deliver. And this electronic disorder, fundamental disorder in organic semiconductors, is actually not that high. It's quite low. They're quite ordered, which means the prospect for high efficiency is very good. And what that means is that it's really low electronic disorder equals a high voltage generated from your solar cell. And we're seeing increased voltages in organics. So they're probably not going to be a silver bullet, but I expect them to continue to improve. And as long as they're continued to be worked on, then they will eventually also probably rise to high efficiency. The other advantage of organics is you can tune the color. So actually for building integrated PV, they could also be quite interesting, where you can absorb in the infrared only.
You can take one last question at the back there.
So one last from non-science guy. I consider all of this course very interesting, but I see, have you ever considered that is the easiest way to get 30% of efficiency? For example, across my house, I use the typical photo installation with the 22, 23 at max on the solar trackers. And so you can cross the 30% of efficiency quite well and without the laboratory. So the question is maybe that the trackers is the future of the photovoltaic installations. Thank you.
I think so. If I just reiterate your question in case anyone didn't understand it, you were suggesting, and rightly, that as well as having a fixed axis, you can also track the sunlight. Of course, it doesn't improve the efficiency, it improves the energy yield, so the amount of power you extract, which will make it equivalent to a 30% efficient cell. I absolutely agree. In fact, we've done these calculations and seen exactly that. Of course, the higher efficiency the cell is, the more sense it makes to use trackers, because you've got more power from the module, so you gain even more. So it offsets that additional cost. So actually, perovskites delivering a 30% flat plate technology, of course, on trackers would outperform your silicon. And it's likely that for many installations, at least single-axis tracking would be the preferred means because the efficiency is higher.
This is a rider to the last question, is it?
So the next question is the last
one.
Not
the next question.
The last one. What we can do with the temperature, because when we exceed the 70%, 70 Celsius, we are out of game. So the question is what we can do with that.
Yeah. So the easiest answer is we'll make our cells 85% efficient, then we extract all the energy and we won't get temperature thermal gain. Of course, that's easier said than done. The more efficient they are, the less heat will be generated, but you're only talking about a 5% difference. This is something we have to, the better the technology and the better the contacts, the less recombination, the less losses at the surface of the material, the better the performance under higher temperature. So you see that all different technologies have a different temperature coefficient, how they lose efficiency on temperature. So that's about improving the technology as much as it is something we have to live with. That's what has to go into the calculation of energy yield. But that is calculated, that's implemented when working out how much power you'll really generate in a different location. So that's actually an advantage of the UK, is the efficiency or the energy yield per absorbed watt will be higher than in somewhere like Dubai, because the cells will be cooler. They actually operate better under cooler conditions.
Thank you. It's for the moment to draw the event to a close. And I want to start by thanking Henry for a wonderful lecture that was wonderfully accessible and has generated that real excitement that there are new prospects, that what in some ways had been seen as an old industry that was settled has been blown apart by these remarkable recent results. I would like to put that in a sort of scientific context. I mean, those who were in the, will remember the early days of the world of germanium and then silicon will recall that we had to do something called zone refining to take impurities out of silicon down below 1 part in a million. Silicon devices don't work if they have chemical impurities at higher levels than maybe a part in a million. The materials Henry has discovered have got impurities at the level of several per hundred. And this is absolutely remarkable. You can take most textbooks on inorganic semiconductors and put them in the bin because Henry's materials, this is a major discovery, are fault tolerant. They don't generate these defect states that you referred to, Henry, for amorphous silicon, non-crystalline silicon. Why they don't is a real surprise. There are some explanations. I wouldn't say there are yet complete explanations, but it has, I think anyone rationally on the basis of half a century of development of inorganic semiconductors, picking up a material that, as you show, you cheerfully take some little piles of orange powder and white powder, and it goes black when you mix them together, and you do it on the lab bench, no one would have suspected that it would make a good semiconductor. And it's that sense of the utter unexpectedness of what you've discovered, and then how quickly that has translated into this fabulous opportunity that makes this so special. So it really is a wonderful moment to celebrate what you've done. I have some things to hand to you. Let me start with a medal. So, Henry, can I...
Thank you very, very much.
And a scroll.
Thank you very much.
And then the one thing you shouldn't lose.
Thank you. Thank you very much.